So our focus is still on addition reactions in this packet of notes, even though we took a little recent side trip to see what we could do in terms of opening epoxides and to relate that to other patterns that we've seen in some of these addition reactions. So let's resume addition reactions and look at the fact that we can make not only anti-vicinal diols using the method described in the previous section, but we can also make syn-vicinal diols. This would be called a syn dihydroxylation because we're adding two hydroxyl groups across the alkene, and they're adding or attaching to the same face of the alkene. To do so, we're going to use a combination of chemicals. This one here, OSO4, we're using in a catalytic amount, which we'll talk about in a minute. This is called osmium tetroxide. And we're going to use that in combination with something like this. So TBHP stands for tert-butyl hydroperoxide. You could also use hydrogen peroxide in this instance. And typically there's going to be some water around there as well. So the result of this is going to be that the two OH groups attach to the same face of the alkene, as I mentioned earlier. So this gives us a complementary pathway to get to a syn diol instead of the anti-diols that we already know how to make. So now we have access to both. Okay, so let's talk about this piece right here, the fact that the osmium reagent is catalytic. So let's talk about osmium tetroxide. Okay, so OSO4. This guy is toxic. It's expensive. And it's volatile, meaning it vaporizes easily. What could go wrong, right? Okay, so what happens is the following. Let's draw a structure of a molecule that's key to you being able to see. Okay, so this one is called 11-cis-retinal. Al, because of the aldehyde functional group, and cis, because of this double bond right here. All the rest of them are trans. Okay, so this is a molecule that's present in your eyes. So what it does is it attaches to a protein in your eye that's called opsin. Okay, so proteins have active sites, and the molecules that bind to those active sites bind to them in such a way that they fit perfectly. So the active site is, if you will, designed for particular molecules or a particular molecule. So when the retinal bonds to opsin, forms a complex called rhodopsin, and when the rhodopsin absorbs a photon of light, so in other words, when you see something and light enters your eye, that cis double bond isomerizes. It isomerizes to the trans double bond. So let's make a note of that over here. So isomerization, when something isomerizes, what that means is that it turns into an isomer of itself. And in this case, it's the cis double bond that's isomerizing to the trans double bond. So cis and trans are isomers of one another. Once it's in the trans configuration, it doesn't fit into the active site in the same way. And this causes a signal to be sent through the optic nerve to your brain that tells you that you just saw something. Okay, so that's involved in your eyesight. Well, if you take a look at what osmium tetroxide does up above, when it sees a double bond, it installs two hydroxyl groups. Okay, now if it does this to all of these double bonds in the 11-cis retinal, that's going to render that molecule incapable of isomerizing from a cis to a trans double bond. So the toxicity of osmium tetroxide is associated with blindness because this prevents you from being able to register that you've seen anything. So it's a good thing that we have things like goggles and gloves and fume hoods in our labs so that you can work with this in a safe manner, which people do all the time. The other thing about it that helps minimize the risk is its catalytic nature. So we can use this in a catalytic amount. So it's time for us to talk a little more in detail about catalysis and about catalysts. Okay, so catalysts in general, as you know from Gen Chem, speed up a reaction, and they do so by lowering the activation energy for the reaction. And they do that by providing an alternate pathway, that is to say, a different mechanism. Another thing that you might remember about catalysts is that they don't get consumed in the reactions that they're in. So they're not consumed in the reaction, but instead they get regenerated. So what does that mean? Let's look at a little scheme. So let's say that you have some chemical we'll call A, and you want to do a reaction. You somehow want A to bond to B. Okay, so if you're doing this with a catalyst, then one way of depicting it might be that you combine A with a catalyst. We'll just call the catalyst star. So let's say in this case, and this would be the case with the proteins in your body, that the catalyst and A form a complex, so they bind to each other. So now we have A star. And let's say that because of that, now B will more readily bond to A. So B comes along, likes what it sees, and now you have AB star. Well, now the catalyst has done its job. So it leaves, so we lose the catalyst, and we end up with the product that we wanted, which is AB. The catalyst can then come back around here, find another A, and enter another what we call catalytic cycle. Okay, so it gets regenerated and can be used over and over again many times. So for that reason, you can usually use catalysts in a much, much smaller stoichiometric quantity than any of the other reagents or starting materials that you have. Okay, so let's look at an example of predicting products for this reaction. So we'll start with this alkene and treat it with osmium tetroxide in combination with either hydrogen peroxide or tert-butyl hydrogen peroxide, hydroperoxide rather, and there's going to be some water. The purpose of the peroxide, by the way, is to help regenerate the osmium catalyst. So what we have here, as we've seen in other instances, are achiral starting materials and reagents. So these are optically inactive. That leads us to expect optically inactive product. This is a syn addition, so the two hydroxyl groups can attach to the front face, which will push the methyl back, or to the back face. Pushing the methyl forward. Because there's no preference for the osmium reagent to attack at either face of the alkene, we get these in equal amounts. These are enantiomers. and they form as a racemic mixture. Okay, let's take a look at another addition reaction. This one's called ozonolysis. Okay, now what we're going to do here, we didn't look at a mechanism for the previous reaction, and we're not going to look at a mechanism for this one or the next one either. So we're just going to look at the bottom line. It is an addition reaction though, because what's happening first is that you're treating the alkene with ozone, which is O3. So what happens is that the ozone itself adds across the alkene, and the product that you get from that decomposes, and that's what gives you the final organic products of the reaction, and that's what we care about. So first of all, let's start out with the premise that ozonolysis converts an alkene into carbonyl compounds. The types of carbonyls that you can make using this method are the following. You can make aldehydes, ketones, and carboxylic acids. So right away, you know that if you're predicting products for an ozonolysis, they're going to be aldehydes, ketones, or carboxylic acids. Okay, so let's talk about some things going on in the reaction. Okay, so I'm going to expand this a little bit so we can see it better. So we have two alkene carbons, so I'm going to just highlight those guys. So the yellow and the blue are the alkene carbons. And what happens in the reaction is that the alkene double bond is completely broken. So we completely rupture that double bond. So we cleave the bond, it's called a cleavage. And then each of the carbons that was in that bond, so each of the alkene carbons, gets oxidized. So this is called an oxidative cleavage. So in this instance, these are the two products that we get. So step one is ozone, O3, and step two is a workup. Now these are not aqueous workups necessarily. They're a little bit different than that. But we'll look at the details of that in just a second. Okay, so what's happening in this reaction? First of all, each alkene carbon becomes a carbonyl carbon. The reaction itself is called an oxidative cleavage. So the double bond is broken. And each carbon in that bond is oxidized. And then finally, what kind of carbonyl product do you get? Do you get an aldehyde? Do you get ketones? Do you get carboxylic acids? The type of carbonyl product you get depends on two things. It depends on the structure of the alkene you start with, and which workup you use. Okay, so let's talk about the two workups. The two workups people generally call a reductive workup and an oxidative workup, but I wouldn't worry too much about those terms, although in some cases they may help you to remember the outcomes. In the reductive workup, we use what's called dimethyl sulfide, which is really, really stinky stuff. That's abbreviated as DMS, and it's two methyl groups flanking a sulfur. So it looks like this. Okay. Or you might also see in different sources, you could use zinc and water. So that's another set of reagents that you could use, and that's going to do the same thing that the DMS workup would do. The oxidative workup uses hydrogen peroxide, so H2O2. Okay, so how does this work out? As it turns out, if there's a hydrogen that's directly attached to one of the alkene carbons, that's where the workup is going to give you a different outcome. Okay, depending on the workup you use, you'll get something different. So let's look at this case here. So let's draw in the hydrogen that's missing. So this is exactly what I'm talking about. This is a hydrogen directly attached to an alkene carbon. So we're going to treat this alkene with ozone and follow it with the DMS workup. So remember what happens. The alkene is broken, and each of the carbons gets oxidized. So to draw the products, from the left side, we're going to have this. And from the right side, we're going to have this. So we get a ketone and an aldehyde. So the important point here is the following. With a DMS workup, hydrogens that are attached to alkene carbons stay as hydrogens in the product. So what that means is that you would generate an aldehyde, at least as one of the products. So let's compare that to the case where you're using the other workup. So let's look at the same alkene. We'll treat with ozone, but this time we're going to follow it up with a hydrogen peroxide workup. The left side stays the same. It's the right side that's going to change. So instead of an H, we now have an OH. Okay, so what we want to point out here is with the hydrogen peroxide workup, H's that are attached to alkene carbons are converted to OHs. That means the product would be a carboxylic acid, at least one of them. Okay, let's look at this example here. Okay, so we're using O3, ozone, and a DMS workup. Okay, so we have an alkene that's part of a ring, but the ozonolysis is still going to happen. So let's put some labels on things. And let's draw in any hydrogens that we need to. Because we're using a DMS workup, remember that means that that hydrogen is just going to stay as a hydrogen. That bond is not going to get oxidized up to an O. So same thing happens. The alkene is going to get broken, and each of the carbons in it will be oxidized. So to draw the product, let's put some numbers on our carbon atoms, like so. And so breaking the alkene, in this case, is going to break open that ring. So we have carbon 1, 2, 3, 4, 5, and 6. Carbon 2 becomes a carbonyl carbon, and carbon 6 becomes a carbonyl carbon. And carbon-6 also still has that H attached to it. So this H here is that one. Now, what if we had used the other workup? Well, in that case, we get almost the same thing, except instead of an H, we'd have an OH. Let's take a look at one more reaction. This one is called catalytic hydrogenation, and this is a syn addition. So what we're doing here is adding H2 across an alkene. The H's are going to add to the same face of the alkene, and this has to take place in the presence of a metal catalyst. So hydrogen gas can add across an alkene, but it takes a very, 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 very long time to do so. And so you need a catalyst in there to kind of help things along. The catalyst is going to be one of 4 metals that are commonly used. So palladium, platinum, rhodium, or nickel are the 4 main suspects that you would use here. So those are your list of choices for the metal catalyst. Hydrogenation itself refers to adding H2 across an alkene. This is a reduction because the product has more carbon-hydrogen bonds than the starting material does. So we're not going to look at a mechanism, but we're going to talk briefly about how you would conduct this, and we'll look at an example of predicting a product. Okay, so what you would do to run this on a small scale in a lab would be the following. So you'll have some little flask, a little round bottom flask with your solvent in it, and an alkene, and the metal. Now the metal is not going to dissolve in your solvent. Okay, so it's going to stay in a different phase than the solvent and then the rest of the reactants. So we call that a heterogeneous catalyst. So the metal here is a heterogeneous catalyst. Meaning it's in a different phase than the reactants. That has a consequence for how the reaction occurs, which we'll talk about shortly. Okay, so to complete this setup, what you would do, if you're doing it again on a small scale, what you can do is just fill up a regular balloon with hydrogen gas and then fit that over the top of the reaction. Okay, now there's much more complicated instruments that you can use to do this, but on a small scale, this works pretty well. Okay, so you're going to fill the balloon with hydrogen and then just put that on top of the reaction mixture. And what we say about that is that that is putting the reaction under an atmosphere of hydrogen. So now the reaction is under an atmosphere of hydrogen. Okay, so what's going on in there now? All right, so you have the only place, because the metal is a heterogeneous catalyst, because it's in a different phase than your reactants, the only place that reaction can occur is at the surface of the metal where it contacts the solvent and potentially the other reactants. So let's say that this is the metal surface, what I'm drawing here. So some hydrogen molecules are going to be able to find their way to the metal surface and somehow become associated with it. And there's different ways to show this. So they become associated with the metal surface, and so that kind of holds them in position. At that point, an alkene can approach this, and then the hydrogens are transferred to the same face of the alkene. So the hydrogen attaches to the metal, and that holds it in position so that those hydrogens can then be transferred to the alkene. And because they're going onto the same face, that is a syn addition. The mechanism for this is actually not an organic reaction mechanism. It's instead under the purview of inorganic chemistry. So it's an inorganic mechanism that doesn't really follow the patterns that we've seen, and so it's outside the scope of our class, but this is generally what's happening without drawing any arrows. Okay, so let's take a look at an example of this. Let's say we have this guy. Okay, so we recognize that what we're starting with is a chiral alkene. Because it's chiral, it's optically active. So let's treat this with hydrogen gas, and then for the catalyst, let's use this. So PD/C. That said palladium on carbon. And what it is that you have palladium metal attached to the surface of carbon. And the carbon that you're using here is graphite. So if you've ever used graphite, say, to lubricate a lock, so you can squirt graphite into a lock to help it work better, then you know that it's a fine, fine black powder. And so the metal can absorb to the surface of that powder. And because the grains are so small, because it's such a fine powder, that gives you a lot of surface area for metal atoms to attach. So you get a lot of catalytic power using this particular type of reagent. So palladium on carbon is a very, very commonly used version of this. So the two hydrogens are going to add to the same face. So the methyl group on the right side stays the same. The hydrogens can either add from the front face, which is going to push back the methyl group up at the top of the molecule, or they can add to the back face, and that pushes that methyl group forward. Notice in both of those products that there's another hydrogen that I haven't drawn at the highlighted carbon. I'm just drawing the ones that are being attached in the reaction. And so if we redraw these to kind of clean things up, because remember we don't always have to draw hydrogens, we redraw the products. That makes it easier to see that what we have is a pair of diastereomers. Diastereomers are formed in unequal amounts because they form at different rates. And the reason for that is because the approach of one face of the alkene by a reagent is going to be easier and a lower energy approach, require less energy than the approach from the other face. So you're going to get more of one product than the other. Okay, and that wraps up this packet of notes.